আমি কপিতে যখন ওগুলো পাঠিয়ে দিয়েছি, হ্যাঁ। এখনো সব আছে। চা চা খাবেন? গুড মর্নিং।
Okay, so yesterday we saw the Vinogradov's proof of the 3' problem. And then I mentioned the 2' problem. And it's a much more difficult problem. But sometimes we can make some links. And I want to show you today one of those links with the Ziegel zeros that you have seen. So, for that, I want to prove something which is called a repulsion formula. A repulsion formula, it says that a repulsion property, let's say, a repulsion property repulsion is the opposite of attraction. So what when there's attraction, something exists, and then because this thing exists, something else comes there. When there's repulsion, something exists, and because it exists, the others go away. Yeah. So this repulsion property is for the zeros. Yeah. So if there is a zero, so this in the philosophy is that a possible zero would force all other zeros away from all L functions possible zero or a possible zero with a certain modulus of the same modulus all other zeros of all L functions of the same modulus away from the real axis. So all other zeros may be real, may not be real. Okay, but if you have an exceptional zero, then you can be assured of a distance between the real axis and any zero that might exist. So that's more profound than it sounds, because we want to. You remember that we did results like Ziegel's theorem and so on. So you have your real axis, and then you want to see how close you can get with your zeros. So if you can bound these, then sometimes what can happen is you can get a contradiction that I have violated some theorem, yeah, and therefore this cannot be true. So these all other zeros, these can be real or complex. Okay. And the aim of the first part is to quantify this statement. So this is known as the, this was originally done long time ago, but I want to give you a more recent proof. Recent means this is a proof of 1987 or 88 or something like that, whereas the others are at least 50 years older. And it is in this version that we will use it for the Goldbach. Okay. Yeah. Well, maybe I'm saying I'm saying more than I mean. It's not that I will use it for the Goldbach. It is this version of the repulsion property which will give a relationship of the Goldbach problem with the Ziegel zeros. Okay, so so we will find a condition when the Ziegel zeros condition on the binary Goldbach problem, which will make the zeros disappear. Okay, the exceptional zeros disappear. So, of course, by now you guess that this condition is not something we know how to find. Because if we did, then we would already know that the Ziegel zero does not exist. So it's going to be a conditional result, that if a certain condition, which is called the Hardy-Littlewood condition, if this condition is true, then the Ziegel zeros do not exist. This is the aim. So before that, I want to prove the repulsion property. Okay, so this is a theorem by Bombieri, and so I will prove this theorem, which is due to Bombieri. Okay, so this says that first of all, so this estimates two things. We have property one. I have n alpha t chi. This is over chi, and the sum is over some q. Okay, which is bounded by a certain capital T, and q is modulo q. This is less than or less than T C3 1 minus alpha. And I will just now tell you what these things mean. This happens if, in general, and two, if there exists an exceptional zero which we will call beta 1, like yesterday and the other days, then this sum n alpha t chi is less than sigma 1 log t t c3 1 minus alpha. Now, I have to tell you what this is chi mod q, and this is q, which is bounded by t. So I have to tell you what these things are. Okay, so the notation is that n alpha t chi, that we have seen earlier. Okay, these are the zeros. So so I would just like to recall, I've used the C3 here, so you can imagine that there should be a C1 and a C2 before. I would like to remind you that these are the things that we will use in the proof. So, so if there's a C3, then there should be a C1. There exists, you have seen this, but we will repeat it. There exists a constant C1, which is positive, with positive such that L S chi is 0 with sigma greater than or equal to 1 minus C1 by log T. T is less than some capital T, that's what is happening there, but it is greater than 2. So, which means that beta 1 is greater than equal to 1 minus, that's my C1 by log T, which is the same thing as saying that 1 minus beta 1 is less than C1 of log T. All right, this is Landau page. Okay. You recall this, then second thing is that, so you need a C2, yeah? You have a C1 and then there's a C2. So for a constant positive C2, 1 minus beta 1 is greater than equal to C2 T to the power half log T, and where C1 and C2 are both effective and computable constants. Are effective, and we can calculate them. So now I will let delta 1 to be equal to 1 minus beta 1, and then last thing that I should say is n, these are the notations. What is this n? N alpha T and chi. This is the number of complex zeros in which are complex zeros where sigma is between alpha and 1, little t is bounded by capital T, and this S is not exceptional. These are non-exceptional zeros. Yeah. So anything else that has not been explained? Yeah, the star. The star means the sum over primitive characters. So this is Bombieri's theorem. Okay. So the proof I follow is from Bombieri's book. This is 1987. The book is in French, so you have to if you want to read it, you have to be a little, it'll take a little time maybe, but yeah. So it's an asterisk blue book, which yeah, it's written in a somewhat old-fashioned style, typed. You know, it's not. It's on a. It's on a written on a typewriter. So you should have a look at it. So the proof that I follow is from that book. Okay. So the reason, as I said, why I used this version of the repulsion property, because it is this version. It is there are older versions. There is Linux version. There is there is the Heilbronn version and other versions, but older ones. But I use this one because I want to show you, at least give you an idea of how it can be used. And another reason is that from this theorem, the Ziegel's theorem becomes completely clear straight away. You don't need any additional work. For free, you get the Ziegel's theorem. Yeah. So yeah. So let me start. So these are things I will need. So that's C1, that's C2. What else do I need? So this proof, the proof will require some lemmas. Okay. Have you ever seen a theorem that does not require some lemmas? It always requires some lemmas, because, well, maybe Pythagoras doesn't require any lemmas. So we require a few lemmas, and I will not prove all of them. I will prove most of them. So the proof of this theorem requires a few lemmas. Okay, so I will at least state them all. So the first one is Turan's lemma, lemma 1. This is due to Turan. Okay. This lemma I will not prove. I will not prove it because it's a very, very long proof, and it's a special case of a very long proof. So I will not prove it. Yeah, you can, if you when you have the time, you should look up a proof. So I take some complex numbers z1 to zn, and these are complex, and I take some capital K, which is a positive integer. All right. Then I claim that, I claim that Turan claims there exists a little k. Okay. This little k is between capital K and capital 2k. Okay. So you choose your big K, you get a little k between capital this, such that if you take the kth power of each of these and sum them up, so z1k plus z2k plus znk, then this can be bounded by z1 power to the power of 50. How he gets this 50, I think is just for fun. To write something nice. And the numbers used in this proof are all very nice numbers: 50, 100, 400, etc. It's not that it has to be 50. Okay, it's something like that. What I mean is, this is not a precise 50. All right, it's something that will work. So there will be no proof of this today. Okay. Then I will give you the density lemma, which we will prove. Bombieri doesn't prove it either in his book. So you'll probably have to find it somewhere else. maybe collected works of Turan or something like that. And then maybe it's written in Hungarian, I don't know. So I don't know really. I mean, I haven't seen a proof. Okay. Okay. So theorem, this is lemma 2. It's called the density lemma. Okay. So this we will prove. All right. So I will take an L function. Okay. Modulo Q. And this Q, the modulus, is bounded by T. Okay. And we will let W is equal to 1 plus IV, and V is also bounded by T. Okay. But V is at least 2 if you have the case that chi is chi0. Okay. Then L of S chi has at most, which means R log T zeros in a circle you have an S here and you have a W here. So S minus W, which is less than or equal to R, uniformly for R between 1/4 and 1 by log T. Okay, so what does this mean? It means that if you have a circle here, so say one is here, and then you have some circle here. So this one has radius, this circle has radius R. Okay, the circle has radius R, which is greater than or equal to 1 by log T. All right, and the zeros are inside this. So there are some zeros here. Are there? And there is a W which is equal to, which follows the, so S is equal to W plus R, which means S is equal to W plus R. Okay, that's what this means. So we will use, what are we going to use? We are going to use L prime by L. Okay. Do you have any questions? Okay. So if S minus W is here, S minus W If it is less than half, then what do we have? Proof. Proof of lemma 2. Okay. So if S is, so in S minus, in this region, S minus 1 less than equal to half, what do we have? We know that L prime by L of S chi, this is bounded, this can be bounded by rho minus sigma less than equal to 1 upon S minus rho plus big O of log of t. Okay. So now I can pull that out, this one, okay, which I do. If I take the sum, rho minus W, which is less than or equal to 1. So 1 upon, now I write this as S is equal to omega plus R. So omega plus R minus rho. This is equal to big O of log t. And then I replace this by its definition. So minus, so this is lambda n. You remember the definition? Lambda von Mongold, lambda n, chi of n to the power 1 plus r plus I times v. This is my v, yeah? This one, and I have this one. Okay. So, this is, let me keep the O of log t. All right. And then what can I do to this one? Can you find a bound for this? Does this can you use a bound? Can you suggest a bound for this? So you know that I can take this to be big O of 1 by R. Why? Because zeta of 1 plus R. Yeah, why? Because zeta of 1 plus R can be bounded by what? Yeah. So 1 upon 1 plus R minus 1. Yeah, that's the reason. So I can bound this by O of 1 by R. Okay. That's the reason. Okay. So you have what do I know? I know that if I take the real part of this, okay, then that's going to be greater than 0. Yeah. So we have, I take real part of 1 by omega w plus r minus s. This is greater than or equal to 0. And so real part of 1 upon w plus r minus 2 minus sigma will be greater than equal to 2 of r if I have the condition that sigma rho minus omega is less than equal to r. All right. Whenever I am in the circle rho minus omega less than equal to r, then this is okay. So so if I take the number of zeros in this in s minus omega, so number of zeros in s minus omega, which is less than equal to r, yeah, equal to say n1, okay. Number of zeros be equal to n, then n1 is less n1, then you have the 2r here, so you normalize by the 2r. This is going to be less than equal to log of t plus 1 by r. Okay, and that's what we wanted to show. Okay. Now I'll give a name for this L prime by L S of chi for a special case when there are no exceptional zeros. So that is, I can allow an exceptional zero, but I will not allow anything else. Okay, so let's prove some small lemma for that. So I will call it fs of chi. Let f s of chi this be equal to L prime S by L S chi. Remember this? We had that. We've just seen that L prime by L S chi. But we will put some condition on this. Otherwise, there's no need to give it a name. So for all chi whose modulus is q and which is bounded, okay, and that means this depends also on t, and let this be equal to 0 if there are no exceptional zeros. And suppose there is an exceptional zero, we call it beta 1, and if there exists beta 1, which is equal to 1 minus delta 1, okay, So this is an exceptional zero. Then f of s chi is equal to this L prime by L, which is, we keep the same L prime by L, S of chi, and plus L prime by L, S plus sigma 1, yeah, the difference here, S plus sigma 1. So you notice this beta 1 being written as 1 minus delta 1, this is giving you the distance from 1, yeah. This is the sigma 1, which is giving you the distance from 1, and this is chi, okay. So let us consider this case where there is an exceptional zero. It's the more complicated case. When there isn't, it's easier. Yeah. So using a known result, this is still lemma 2. Okay. So L prime by L S of chi, you have seen this several times over. This is the sum of 1 upon S minus rho plus, this is, we will, let us consider, so let us consider the case with beta 1, case where beta 1 exists. Okay. So you have S minus rho, and then you have 1 upon S plus sigma 1 minus rho prime. Okay. So here, S minus rho minus omega is less than or equal to 1, and S minus W is less than equal to half. W is 1 plus IV, and V is less than or equal to T. These are the conditions that we had in the beginning. V is greater than or equal to 2 in case chi is chi 0. All right. And the second one, these are the zeros. And rho prime, the second sum, this one sum, two sums, so that's the second sum. The second sum with zeros, rho prime of L S chi chi 1, that's the one here, okay. And this time, rho prime minus sigma 1 minus W is less than or equal to 1. Now, supposing chi is equal to chi 0.
So it should be f of, I mean, if the function is chi, right?
Yeah.
There also should be like when the proof of lemma to continuity. We are writing the left side L prime by is L prime by or should be like capital F in terms.
Ah.
Because we have
Yes, 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 yes. So supposing I have chi is equal to chi 0. So what happens if chi is chi 0? In the case where chi is chi 0, what happens? This minus 1 by S minus 1 is a pole of L S chi 0. Yeah?
should be like capital F instead of capital L, and there should be some other term, right? It is not only the sum over 0.
Yeah, that's
Like
why that is why I said that we could have L prime by L.
No.
Uh,
That would be capital F of S comma chi
oh,
instead of capital L.
yeah.
I'm saying that,
Yes, yes, yes. That's the one.
there
Yeah.
should be also some big O term, right? Like not only sum over zeros, like big O of log t or something.
Wait, let's get it correct. So f of s chi is L prime by, but f of s chi and L prime of s chi are the same if there are no exceptional zeros.
L prime by L is something like sum over zeros plus there is some more
Some more terms. Yeah.
like big O of log t maybe something.
Yeah. So I'm sorry, there should be an error term. Big O of, yeah. How bad, how crude can the error term be?
I mean, S is inside the circle,
Yeah.
center W, and W is like over 1 plus something.
Yeah.
Like log t, maybe.
Yeah, should do. Yeah, I think so. You're right. Thank you. So if chi is equal to chi 0, then what happens? Then minus 1 upon s minus 1 the term, which is this term, minus 1 by s minus 1? What does it correspond to? Minus 1 by s minus 1? What is it? This corresponds to the pole. Yeah? This corresponds, then the term minus 1 by s minus 1, which corresponds to the pole of what? Which pole is it? Of whom? L S chi 0. Okay? This is what happens to this one. This gets eaten up by because of this condition. Yeah? If V is greater than equal to 2. Yeah? V is greater than equal to 2 if chi is equal to chi naught. This is the condition that we are supposing. So this is absorbed by the error term. Yes, of course, if I'm talking about an error term, then I better have an error term. Yeah. Thank you. So, yeah. But I could also have written it as L prime by L. I could still have written it by L prime by L. The F. I could have still written it.
But L prime by L is something like someone.
Yeah, that's right. So this is absorbed by whom? By the error term. This is my error term. In the case V is greater than or equal to 2, but that's what we suppose, okay? And if chi is chi1. All right? So chi1 this is equal to chi1 square, and that's equal to chi0. So, so the pole of this time, first time you have the pole of Ls chi0, now you have the pole of Ls chi1, yeah? So that gives you L of S plus delta 1 chi1 at this place, which matters, that is 1 minus sigma 1, which is beta 1. This, what happens to it, the pole of this is compensated. What do I mean by compensated? I mean there's a cancellation by the 0, which is beta 1, of L S chi 1. Yeah? Because in one case you have, see, you have minus 1. I'm looking at these terms which are 1 upon minus 1 upon S minus 1. So here you have what do I mean by what do I mean by the compensated? Yeah, this means in one case you have minus 1 by minus 1 by S minus 1, yeah, and this is 1 minus sigma 1, yeah, plus sigma 1 minus 1, and the other one is 1 upon 1 minus sigma 1 minus 1 minus sigma 1. So this one is my S, 1 minus sigma 1, yeah? And so the minus and the plus, they cancel out. All right?
It's not clear, like
Which one?
the whole sentence for chi equal to chi naught. The first term is like the 1 by S minus 1.
Corresponding to the pole of Ls chi is absorbed by the error term.
Okay, I mean, okay.
Because it enters into the error term.
Mm-hmm.
Okay? And if chi is equal, this is the second term, okay, chi is equal to chi1, then the pole of, or one pole and 1, 0, they cancel each other. So what's the problem with that?
No, I mean, last you were replacing something like 1 by 1 minus delta 1 minus 1 minus.
What you need is a bound. You don't need a precise results.
I mean, last.
Where? This one?
1 minus delta 1 minus 1 minus delta 1. Okay, 0.
1 minus delta 1 is just beta 1, yeah?
What kind of 1 by 0 is replacing it? Maybe clear.
Okay, how many lemmas are allowed per theorem? How many can we expect here? So I will do 3. Okay, I promise I will do 3. The first one I won't do. I will leave it as it's long. It's same as, similar to, can't be same of course. It's just similar to the third one. So here is my lemma 3. Yes. Chi1, this by which your induction takes place. Remember right in the beginning that if you didn't have things that were principal, then they would be induced by some t. Okay. This chi1. Yeah, this is the exceptional chi1. Okay, it's the exceptional chi1. I thought. Yeah. Yeah. Now, I told you that the bounds here are all nice. Yeah. So I'm going to take R to be something between 10 to the power minus 4 and 1 by log t. All right. So, and I will take some k, which is bigger than some, what was my last constant? C what? What was the last constant? How many C's have we used? 3? C3? C4 then, okay. C4 R log t, okay. Omega is 1 plus IV. V is less than equal to T. V is at least 2. If chi is, so the same sort of conditions. And chi has modulus bounded by q less than equal to t. Okay, we'll call it lemma 3 because we've called the other two. The first two lemmas, we've called them lemmas 1 and 2. Okay. Yeah, I haven't finished stating the lemma. Nothing has happened yet. These are the conditions. Then what happens? So if the function you haven't missed much, just 2 lemmas. So if what happens, if the function ls chi has a non-exceptional zero. Okay, so what's a non-exceptional zero? A non-exceptional zero, what is it? Trivial? No. Trivial zeros are not interesting here. I mean, they're never interesting, total zeros. So, no, non-exceptional means you remember what exceptional zeros were. I mean, we showed that there can be at most one exceptional zero in a certain place, it doesn't mean that there is only one possible zero, right? It just means that if you can somehow control the situation, then you have 1 0, and this one is called the Ziegel zero or the exceptional zero. So it doesn't mean that there are no other zeros. That is what I told you before, that if you can show that there is a Ziegel zero, you will show that the generalized Riemann hypothesis is false. But if you show that there are no Ziegel zeros, you do not prove that the generalized Riemann hypothesis is true. You just say that it is probably true. Okay, so there can be other zeros. So there can be some other zeros. It's not trivial. It's a non-trivial zero. Okay, so LS chi, if the function has a non, so my statement is not yet over. In this area, in Z minus S minus W, which is less than equal to R, then you remember the first lemma that we stated, there was a K between capital K and capital 2K. So that's going to come up now. There exists a K, which is a positive integer. K is between capital K and 2K, such that what happens, you have 1 by factorial K derivative of kth derivative. This is the kth derivative of f. That's my f, the f that I had defined, L prime S chi by L S chi, f of W plus R chi. This one is less than equal to 200. Again, I told you this, all the constants are somehow rounded up and made nice, and because actually how much do I care whether it's 200 or not? Okay, 200R minus K plus 1. Minus 1. So does this remind you of something? This kind of a result? You have a kth derivative, and have you seen such things in earlier in life? Not about L functions, not talking about L functions, some function, just think of this as being some kind of some function. Have you seen such things? Yes, where have you seen them? Huh? These are you use the Cauchy's theorem, yeah. So Cauchy's inequality, okay. So the proof will be to use. So proof, this is lemma 3, okay. It's lemma 3, and we will use Cauchy's. Of course, you can already get that over here we are going to use Turan's result. Yeah, you can guess that. We didn't write it for nothing. So we use Cauchy's inequality for derivatives of what kind of, when can we use Cauchy's inequality? Can we use them for any function? No. What kind of functions? You can't bring arbitrary functions and do them. They have to be holomorphic. Okay. For derivatives of holomorphic functions. Okay. So yes, what do I get? Okay. So then we get -1 to the power k okay 1 by factorial k derivative, kth derivative of f s chi. This is equal to the sum of the zeros 1 upon s minus rho to the power k plus 1 plus rho prime. This is the 1 upon s plus sigma 1 minus rho prime. Okay, plus some big O of 4 to the power k log t. Okay, so here I am now going to localize. So let S0 be equal to W plus R, and this is equal to 1 plus R plus IV. Let lambda be equal to AR for a constant, for a constant, but at least 1. Okay, it can even be equal to 1. Now you're going to do what? We have used 2 lemmas. If you haven't followed all the details of the proof, that you can do later, but you should at least know what the statements of the lemmas are. Which statement can which lemma can I use now of the 2 that we have proved till now? We will. Which lemma can I use? Does this look like something that one of the
That number of zeros in circle followed by log.
Yeah, so that's the density lemma. Okay, so use the density lemma. Don't worry, we are going to use all the lemmas. We didn't create the lemmas for nothing. So yeah. So yeah, I don't know where the word lemma comes from. You know the German word for it? Hilfsatz. So that's clear. Then it's something brought to help you. But lemma, I don't know. Probably it's Latin. So we use the density lemma. Now use the density lemma. What happens when you use the density lemma? So do you have some intuition about why we have this 4 power k? From where do you think the 4 power k turns up? There has to be some kind of dyadic decomposition. Okay, usually when you get this kind of powers of 2 landing up like that, from which you're going to break this up. Yeah, so so you take your rho minus w, you take this between 2 to the power j plus 1 and 2 to the power j omega. All right, and use the density lemma on this for whom? For this one, you have 1 minus S0, okay? So you take the sum now over the zeros, but at this point over the zeros, and you take this out 1 upon S0 minus rho, this one, S0 minus rho at K. This time it has to fall, right? You have K plus 1, so yeah. Yeah. Now then what will happen? Take the derivative. So that's where I want to arrive. So minus 1 power k, 1 pi factorial k, derivative this one k, f s 0 chi. Okay. S0 chi. Okay. This will be equal to, write out the definition, 1 upon S0 minus rho k plus 1, take the derivative of this, plus the second term, derivative of 1 upon S0. The second term, it's no longer on the board, but remember this one was delta 1 minus rho prime, okay? And this is k plus 1. So the first one is over rho and the second one is, and then you have a big O of lambda to the power minus k log t. Okay. So in which case will this be true? This will be true if lambda is less than equal to 1/4, because that was a condition in the lemma. And this one, so I have sigma there, sigma minus, no, so rho minus W, this should be less than or equal to lambda, so, and this one, rho prime minus delta 1 minus omega should be less than or equal to lambda also. All right. Now you've done this. So what do you want to do now? So you see we have broken this into two parts. We have taken between 2 to the power j omega and to the power j plus 1 omega. So you should do it repeatedly. Okay, you use the density lemma again. All right, density lemma, use it again. And if you do that again, the repeat the use of this till
So how do you start partition? Was complex.
who is complex? Omega, what was, oh yeah, what was omega? Omega was 1 plus IV, I think, wasn't it? Yeah. So what's the problem with it?
that same. The 2.8 megabits.
Already ordered. Left side and right side.
You take the principal part probably. I don't know. I think so. I think you choose a, huh? Yeah. Yes, I think so. I think so. Should believe that. So if you do that again, you use the density lemma again. If you do that, what happens? You get the number of terms for n terms. Then you get n is bounded by lambda log t. N is the number of terms. Because every time you get a bound, then for the number of terms, you get lambda log t. Now you can use the first lemma that we talked about, which is Turan's lemma. Now use Turan's lemma. So for using Turan's lemma, you will have to choose some capital K. And it says that if K is greater than or equal to N,
No, that omega could be replaced by lambda. It will basically not circle of lambda. So that should be lambda. Depending on lambda, you are dividing into that difference, then summing over.
for the first time the density lemma should, when the first time the density lemma, yeah. Because this doesn't make sense. Now I agree with you. Is this okay?
That's left and right. That
Yes, wait, let me just, let me, yes, of course. I mean, that's why you created the lambda here. This is why you created the lambda here. So that's fine. This is fine. That was your problem. I understood. I understand now what your problem was. I was thinking lambda, but I was writing omega. So that was the problem. So my head and hand were not coordinated. So now I want to use the Turan's lemma. Who's going to help me with Turan's lemma? So what was Turan's lemma? What was it?
We consider a set of complex numbers that capital K,
Yeah?
then we can find a small k from capital K to K.
Yes?
The sum that Z1 to the power K. Z to the power, this was bounded by something. X mod Z1.
Something, yeah. Okay, so let's do that. So if I take a K, if I take some capital K, which is greater than or equal to this N, okay? We take this, then there exists some little k, which is between capital K and and capital 2K. It's so such that what happens if I take 1 upon factorial K, this was my beginning of K, f of S0, then this should be greater than or equal to, so that was 50 for the way it was stated was 50, and you can take it here as 0 minus rho 0, okay, to the K plus 1 minus, there'll be some more terms, O to the lambda minus K, because I have a K here, okay, this is going to give me a lambda minus K log T. All right. So what is rho 0? It is a non-exceptional 0. That's what, do you remember? We said that what happens if there is one. So, yeah. So rho 0 is a non-exceptional 0 and LS chi. So rho 0 is a non-exceptional 0 in L S chi with S minus is less than equal to lambda. So if there exists a rho 0, then with rho 0 minus omega less than equal to r, then what happens? Then S0 minus rho 0 should be less than equal to 2r. Okay. So now I want to do something with this 1 by 50 S0 minus rho 0 K plus 1. So this one, I want to bound this, yeah, the right-hand side of this equation. So I want to bound this. So 1 by 50, it's this 1 by 50, S0 minus rho 0, K plus 1, okay, minus this term, an error term, O K to the power, lambda to the power minus K log of T. This is going to be greater than or equal to, what you get here is, this is 2r, therefore 1 by 100, 50 becomes 100, 1 by 100, K plus 1 by 100r, K plus 1, and this remains the same, lambda to the power minus K log T. Choose some A, let it be more than 200. So if you choose your A, take it to be more than 200, then you get 200 here from that, so 200 divided by a to the power k. This is, remember, little k was less than or equal to 2 times big K. So this one can be written as 200 by a to the 2k, and that's less than or equal to 200 by a. What was our constant? C4. C4 R log T. All right. So I need 2 times this. So I choose A to be equal to 400 to conclude. All right. Hmm? Hmm? Where is the problem I haven't figured out? Yeah? Yeah.
And it should be only K instead of 2K. Then
Ah. Yeah. Yes, because it's greater than little k is greater than k. I'm sorry. Yeah. I'm sorry. Now, yeah. So I have to finish this proof one day, right? I will state lemma 4 and not prove it. All right? Oh, you look so happy. I'm not going to give you a proof of lemma 4, but it's similar to lemma 3. Yeah. In Bombieri's book, these are called lemmas A and B. This is probably the first time we are doing a theorem of some contemporary person, right? Did we do anything else? I mean, we know Grozov and all that, we haven't seen them. Grozov proved it in 1937, and Landau is a picture somewhere. Yeah, is it? No, I think this is the first time. So the statement is long. The proof is also long. I will not do this proof. Okay. So this is now another lemma. So lemma 4. And then I promise you that's the end. If we have lemma 4, then we straight away now go to Bombieri's theorem. Okay. So here is lemma 4, which uses lemma 3. Okay. And nothing else really. It uses lemma 3 and Cauchy's inequality, or all of that you know. So I take some r, which is between 10 to the power minus 4 and 1 by log t, and you take your omega and v as before. Okay. And then you claim that there exist positive constants A, B, C, and C5 positive, all of them positive. In fact, the big A should be a little bit better, such that if LS chi has a non-exceptional zero, you remember that is, we talked a few minutes on that, non-exceptional zero in S minus W less than equal to R. For all x, which is large, greater than t to the power b, because then this integral, this time you have a result with an integral between x and x power a, and you have a sum between y and x of AP. I will tell you just now what AP is. P to the power W. W is the W of the lemma 4. Chi of P. This thing is square dy by y. This is less than or equal to C5, some positive constant C5, and effective. These are effective constants, okay? They can C5 log x cube x to the power minus A, B, what are my constants? A, B, and C, so CR. Okay. So what is AB? AP? AP is, I'm claiming that it has a non-exceptional zero, but I'm not claiming anything about exceptional zero, therefore I have to do the case distinction. So AP is equal to log P, if there are no exceptional zeros, this AP is log P if there are no exceptional zeros or no exceptional character, which is the same thing. If no exceptional character exists, and if it does, then you add a factor for it, log P to the power 1 plus, this is your exceptional character, chi 1p. This is your exceptional p to the delta 1, if not. All right. So no proof given. Today. Okay. Does not mean that there is no proof. But the only thing that's used is lemma 4. Lemma 3. Use lemma 3 and Cauchy's inequality. Okay. So if you are stuck, then you read Bombieri. (1987 or 8, I don't remember. Okay, it's an asterisk notes. So this is, it will be called lemma B in this. Okay.
Statement is it less than equal to should be greater than equal. And
For
then I to C5 now. X cube.
no, it's less than equal to.
Bombay, that is greater than equal.
Is it?
Yeah.
Well, since I haven't written the proof, wait, let's see what lemma 3 does, okay? Lemma 3, in lemma 3, yeah, so if you use, yeah, okay. But that will create a problem, right? Ah, no, it won't. It won't. Sorry. Yeah. So, yeah, with some luck, we will now finish the proof of. Now we have done. Now you can assume that you know all these lemmas, okay? Assuming that you know lemmas 1 to 4, we can prove, and the two theorems which we stated before, that is Landau-Page and the zero-free region. And assuming this, we can now prove theorem, Mombier's theorem, which I stated in the, I did, right? I stated the theorem. So now proof of Mombier's theorem. This is theorem 14 in his book, okay? So now we use Landau-Page and we assume that we can assume, so we are counting the zeros, right? So we can assume that our alpha is less than equal to 1 minus some constant that was C1 by log T. Okay, because what would happen if it were not, if by then, okay, if not, if it were not the case, then n would be 0, all right? N alpha T chi would be 0, yeah? So n, if you take an alpha bigger than that, alpha T chi is 0, so it's not interesting. We look for some, we can forget this altogether and then move to the next page. So now we will take rho to be equal to beta plus I gamma, and this will be a non-exceptional 0 of Ls chi, okay? Be a non-exceptional 0, and we will show that there will be some contradiction. Non-exceptional 0 of Ls chi for what? For beta, which is bigger than alpha. All right? So we are going to take some radius now. we will take our little r to be, which C are we at? We had C6 last, did we have C6? C5? Then C6. C6, 1 minus alpha. Okay, and this constant is at least 2. C6 is at least 2. And this was the C1 that we had, the C1 from Landau page. So this, it's greater than 1 by C1. Okay. So our R is now between 10 to the power minus 4 and 1 by log t. When does this happen? This can happen if alpha is greater than 1 minus 1 upon C, because 1 minus 1 upon, so this constant C, and then the other bound that we had, which was 10 to the power 4. Yeah, it was 10 to the power minus 4. So we will assume this, okay? That, let us assume this. Let this be true. If this is true, then if I have rho minus 1 plus IV, this is going to be less than or equal to 1 minus beta plus gamma minus V. And this is less than or equal to R by 2, because R is, and then I need to bound gamma minus V. This is also R by 2. So the whole thing is less than equal to R if gamma minus V is less than or equal to R by 2. All right. Now use the last lemma, which said by which you could bound your, yes, it was greater than, I remember, now I can. So use lemma 4. What happens when I use lemma 4? So I take the integral between gamma minus R by 2 and gamma plus R by 2. All right. I take the sum between x and y of AP that was done in the, there is our AP, it's still there on the board, p to the power 1 plus IV, okay, lambda p, this whole thing square, dv dy by y, and you go on an integral between x and xa. Okay, so this is going to be using lemma 4. Okay, this is bounded by r log x cube x to the power minus CR. Okay. Now you take the sum over the zeros. Okay. So that was our aim in the beginning. Do you remember? So we take the sum over the zeros. And you get, so our modulus is bounded, and then we have the n. This was the number of zeros, alpha t chi. This was our number of zeros, and the sum was for all q which is less than equal to t. And this, once you have done a little simplification, this is going to be less than x to the power cr log x cube x to xa. I'm just copying y to x. I'm just copying from over there. Y to something went wrong. No, it's something went wrong because it's y to x. Okay, copy it again. AP square p square, and the bit of calculation shows that this is p plus t to the power 5 dy by y. Okay. So could we stop here? I'm very tired. I've been talking for a long time and drinking this chalk. And then I want to show you a bit of the end. And then I want to tell you why I made you suffer so much. It was because something good will happen at the end, and that this repulsion. First, there are two reasons I made you suffer. I made you suffer because then you would have seen a proof completely. And then I will use it for the goal, for the equivalence, not an equivalence, for an implication. It's not an equivalence, for an implication on the non-existence of single zeros. And that is a very recent result. It's 2 years old, okay? By all living mathematicians. I mean, a result that's 2 years old is usually by living mathematicians. One among whom is a very young person. So that's to tell you that I mean, mathematics is going on. It's not over. It's not over with Riemann and Landau. Okay, so let me just stop now and go on after lunch. Okay, then we can, if we still have some time, we can do some exercises. What happened to this? What were we doing? Somebody's Vaughan's lemma, Vaughan's identity.
I forgot to check.
Okay.